Hi students, today we are going to see finite word length effects along with the errors due to input quantization by analog to digital converter. So register are the basic storage device in digital system where we are going to store the filter coefficients. The maximum size of the binary information can be stored in a register. It's called register word length. So for storing input data in the register, they have to be quantized to be coded into binary, and it depends on register word length. So this quantization and coding will introduce error in the input data as the analog data has a infinite precision is converted into a digital data which has finite precision. So infinite precision is converted into a finite precision, which means we are going to lose something. For that, an error will be definitely introduced into the system. So while performing computation, the results may exceed the size of the register used for storing the results. Then the results should be truncated or round off to accommodate, which makes the system non-linear and leads to limit cycle behavior. So the effects of truncation and rounding can be represented in terms of additive error signal, which is called as a round-off noise. So effects due to finite precision representation of a number in a digital system are commonly referred to as finite word length effects. So some of the finite word length effects in digital filters are errors due to quantization of input by A to D converter. So here initially the for the digital system, the input should be digital, but we have analog input. So this analog input will be converted into digital before giving us an input to the processor. So the error will be introduced by due to the quantization of input data by A to D converter. Then errors due to quantization of filter coefficients. So the filter coefficients, after finding the filter coefficient, it should be stored in the register for future calculation. So while quantizing that filter coefficients also, errors will get introduced. It is due to rounding the product in multiplication. So in IIR systems, while obtaining the product in multiplication, due to rounding, the error will get introduced. And errors due to overflow in addition. The last one will be your limit cycle. So errors due to quantization of input data by analog to digital converter. So the process of analog to digital conversion involves sampling the continuous time signal at a rate much greater than Nyquist rate and quantizing the uh, amplitude of the sample signal in a set of discrete amplitude levels. So E of n will be equal to quantized signal minus unquantized signal. So the quantization is uniformly distributed and the mean value of error is 0. So the power of a quantization noise is given by expectation of square of your error signal minus expected square of your error signal. So here the mean value of error signal will be 0. So the variance of your input signal will be expectation of your square of your error signal. So quantization step size is given by r divided by 2 power b. So here the r is nothing but the range of your analog signal which is to be quantized. Suppose if the range of your signal is not given in the problem statement, so the default range will be 2. That is, we are going to consider your binary. The quantization error for rounding will be in the range of minus q by 2 to plus q by 2. So the variance of an error signal is given by, so the variance of x is given by 1 divided by x2 minus x1 integral x1 to x2 x square dx. So here it will be your q by 2 minus of minus q by 2 integral minus q by 2 to plus q by 2 e square of dE. So by integration, you'll be getting e cube divided by 3 and then upper limit minus lower limit will fetch you square q square divided by 12. So the output quantization noise, output noise power due to your quantization of error signal. Your x of n will be added with your error that to get your quantized value of your input and multiplied with your h of n will give you the y dash of n. So this q dash of quantized value of your input x of n can be obtained by x of n plus your e of n. So this can be written as x of n into h of n plus x of n into e of n into your h of n. So x of n into y h of n is obtained by y of n and e of n into h of n can be given by epsilon of n. So variance of your signal is called as output noise power or steady state output noise power due to your quantization of your signal. So that is obtained by my product of your variance of your input signal into summation n equal to 0 to infinity h square of n. So summation h square of n can be obtained by the Parseval's theorem. 1 divided by 2 pi j contour integral h of z inverse into z inverse into dz. So here this contour integral, closed contour integral can be evaluated using your residue theorem for the given poles. So the pole should always lies the poles should always lies inside the unit circle. For the recursive filter shown in the figure, the input x of n has a peak value of 10 volts represented by 6 bits. Compute the variance of output due to A to D conversion. Here, the bit is given by 6 and then your range is 10. So instead of your 10 volts, sometimes they may give -5 to +5 volts. Or if they didn't mention anything in the problem, the range is going to be 2. Default is going to be 2. So compute is the variance of your output noise due to your A to D converter. So the quantization step sizes R divided by 2 power B. R is 10 and B is 6. So quantization value step sizes obtained. So variance of your error signal is Q square divided by 12. So Q value is obtained. So Q square divided by 12 will fetch you the variance of your error signal. Now the variance of your output steady state noise, to calculate that you need your H of Z. So from the figure you can write your difference equation as y of n is equal to x of n plus 0.93 y of n minus 1. So by taking the z transform, I can get my h of z as 1 divided by 1 minus 0.93 z inverse. That is, take all your y of z one side, x of z another side, y of z divided by x of z will fetch you the h of z. So your h of z is z divided by z minus 0.3. So h of z into h of z inverse into z inverse should be found out to find by for the residue theorem. So h of z into h of z inverse into z. So here you have two poles, z minus z equal to 0.93 and z equal to 1 by 0.93. So this one will be considered as this one is greater than 1. So the residue of this value can be obtained by z minus 0.93 into your h of z inverse into z inverse for your pole, z equal to 0.93. So these two things will get cancels each other and substitute your z value as 0.93. So the value can be obtained here. So this should be multiplied by the variance to get your steady state noise power due to your A to D processing. Thank you, students. Have a nice day.